In this video, we talk about stoichiometry using gas laws. So stoichiometry was first introduced in chapter 4 with doing it using mass to going from one mass of one compound to a mass of another compound. So basically stoichiometry is just relating different amounts in a chemical reaction. So in chapter 4 we did this where you were given a mass and they wanted to know what the mass produced or the mass required was. This time, since we're using gas laws, we're either going to be given a volume and asked for a mass, or we're going to be given a mass and asked for the volume. So we're going to be going diagonally this time. But either way, whenever you see the word stoichiometry, you need to realize the fact that you have to go to the moles. And so if it's the mass divided by the molar mass, or for the ideal gas law, it's the ideal gas law is PV is equal to nRT, so it's PV divided by RT, or the volume is nRT divided by P. Okay, we're going to do some problems with that. My computer just locked up. Okay. So in this problem, it says magnesium burns in air to produce magnesium oxide and magnesium nitride. Magnesium nitride then reacts with water to give off ammonia. And it gives me a balanced reaction of magnesium nitride plus 6 waters goes to form 3 magnesium hydroxides plus 2 ammonias. It asks what is the volume. So just like I've been doing all semester, I'm going to have what it's asking for. At 24 degrees, and this is, I want to write down this time what it is. So this is NH3. I have a temperature of 24 degrees C, and millimeters of mercury is pressure, so 753 millimeters of mercury. Will be produced in grams as a unit of mass, so I have a mass of 3.93 grams of magnesium nitride, which this is the magnesium nitride, so Mg3N2. So it's important to realize that I have 2 different compounds in my data. And because I have 2 different compounds, that's what's going to clue me in that it's stoichiometry. And it's stoichiometry with the ideal gas law because I have a volume, a temperature, and a pressure, not just masses. So I'm going to rewrite the balanced reaction down here because I think with stoichiometry it's always easier to write the information down underneath the compounds. It makes it, to me, a little bit easier to see. So magnesium hydroxide plus 2 NH3s. So this is the volume that we want. And I'm going to go ahead and write down the temperature of 24 degrees C and the pressure of 753 millimeters of mercury. And we have 3.93 grams of this. And the reason I think that it helps to write this way is I see very clearly that 2 different compounds are related. Now, I either, for the ideal gas law, which is PV is equal to nRT, I have to have both V and N, or I may have to have either V or N, and I don't have either one of those. So my starting point is going to be at the magnesium nitride. And in order, we did this in chapter 3, in order to find the moles of the magnesium nitride, then it's going to be, I need the molar mass. So the molar mass is 3 times 24.31, and that's magnesium, plus 2 times 14.01, and that's my nitrogen, and that adds up to be 100.95 grams per mole. So my N of Mg3N2 is the mass divided by the molar mass, so it's going to be 3.93 grams divided by 100.95, and I get 0.03893 moles of Mg3N2. Now that I have moles of this, I can relate using the balanced equation to moles of NH3 or ammonia. So I have 0.03893 moles of Mg3N2. And with stoichiometry, the one I'm going to is always on top, so I have 2 moles of NH3. And that 2 comes from this coefficient right here, to 1 mole of Mg3N2. And that comes from the fact that there's no coefficient there. And when I do that, I get 0.07786 moles of NH3. So now I have an N. Okay, so now I have everything I need for the ideal gas law. You do need to remember that the ideal gas constant is 0.0821. I'm going to change colors so I don't get them mixed up here. I'm going to go back and use this white space. So the ideal gas law is PV is equal to nRT. So I have a pressure of 753 millimeters of mercury, but that has to be in atmosphere. So I'm going to do that here at 760. And I get 0.9908 atm. My temperature has to be in Kelvin, so I add 273. That's going to give me 297 K. It's already volume in liters, so, and I have N in moles and R is R. So my pressure is 0.9908 times V. My moles is 0.07786. R is the constant of 0.0821. And my temperature is 297. So this gives me 0.9908 V. When I multiply this side together, I get 1.899. So V is going to be 1.899 divided by the 0.9908. So my volume ends up being 1.92, and the unit is liters. And so that is my final answer. Okay? So that's given a mass and ask you to find the volume, which is what the textbook tends to focus on. But there's nothing to say that it can't ask what mass is required if I'm given a volume and pressure and temperature. So I'm going to show you that one is next. Okay? And so it says nitric acid is produced from nitrogen monoxide, which is in turn prepared from ammonia by the Oswald process, and gives me the balanced reaction. 4 ammonias plus 5 oxygens goes from 4 nitrogen monoxides plus 6 waters. Okay, I have liters, which is a unit of volume. Let me go back to my original color. I have volume of 3.35 liters, and that's O2. I have a temperature of 35 degrees C. I have a pressure of 2.15 atmospheres. Is needed to produce what mass? So we're looking at mass is equal to what of nitrogen monoxide. Okay. So again, I'm going to write down the balanced reaction. 4 NH3s plus 5 O2s goes to form 4 NO plus 6 waters. So my volume is specifically oxygen, so it's 3.35 liters. Temperature and pressure also typically goes with the same thing that I have this for. So I have 35 degrees C and 2.15 atmospheres. And it wants to know the mass, so it wants to know what X grams is for the NO. Okay, so again, to me this very clearly states what it is that I need to do here. Whoops, this is O2. I just made a mistake. I wrote it under the wrong thing. I wrote it under ammonia. Sorry. 3.35 liters, 35 degrees C, and 2.15 atmospheres. Sorry. Okay, so since I have my volume, my temperature, and my pressure, I can find the N. Okay, but of course my temperature has to be in Kelvin, so plus 273 gives me 308 K. And anytime I use the ideal gas law, I have to have R, which is 0.0821, and that's just because that's a constant. Okay. So using the ideal gas law, I have PV is equal to nRT. I have my pressure is in atmosphere, so I have 2.15 liters. Not liters, atmospheres. I'm not going to write it anyway to save space. My volume is 3.35. N is what I'm going to be looking for. R is the gas constant of 0.0821. A lot of times you'll see on the references it's 0.06. My temperature is the 308 K. So when I multiply these two terms together, I get 7.025. Oops, I skipped a digit. 7.2025. And when I multiply these two together, I get 25.29 N. So I divide both sides by the 25.29, so 7.2025 divided by 25.29 is equal to N. So N is 0.2848 moles, and this is of O2. Okay, but I need to relate this to NO. So I have 0.2848 moles of O2. And the one I'm going to is always on top, so it's 4 moles of NO divided by 5 moles of O2. So it's doing that a lot today. And that gives me 0.2279 moles of NO. Okay? And from chapter 3, to go from moles to mass, I need the molar mass. So the molar mass of NO is simply 14.01 plus 16 to give me 30.01 grams per mole. And from chapter 3, okay, you need 0.2279, the moles times the molar mass of 30.01, and that gives me 6.84. Oops, that's 4, not 9 grams of NO. And that is my final answer. Okay? And so that's stoichiometry. And since these were all gases in this equation, we could have gone between any one of those, just like we can in stoichiometry from chapter 3. We just need to know the volume, the pressure, and the temperature of the gas that we're looking at, or going to. And that is the end of this video.